Hello future engineers, welcome to my YouTube channel. If you're still new to my channel, please don't forget to like and subscribe if you like my videos, because I'm going to design this channel to be a one-stop channel for civil engineering and non-civil engineering students. And to keep me going, to keep me refreshed and energized, please share my videos to your friends and to your friends' friends. That's the only way you can also help me promote my channel. So this video discusses about the generalized Hooke's law, and we will define Poisson's ratio. Then we'll develop formulas for uniaxial stresses and strains, biaxial stresses and strains, triaxial stresses and strains. And we'll have two examples. One is not actually part of this topic, only the other part, but it is still part of strain. So let us discuss the generalized Hooke's law and define Poisson's ratio. So Poisson's ratio, denoted by this symbol, is the ratio of the lateral strain, uh, strain sub L, to the longitudinal strain, strain sub T rather, to the longitudinal strain, strain sub L. Whenever the member elongates, it also contracts in the transverse or lateral direction. So if this is the member and it is subjected to um, tensile force on the along the x-axis, then it will contract towards the y and the z-axis respectively. So this is now the deformed shape after the tensile force P is applied. So this is the lateral strain, and the longitudinal strain will be along the x-axis. So a negative sign is preceded in the ratio because the transversal or lateral strain will be negative to make the Poisson's ratio positive. So that's the definition, called that equation 2.8 definition for mathematical expression for Poisson's ratio. In general, with respect to the coordinate axis shown above, the Poisson's ratio is equal to negative strain y over strain x, which is also equal to the negative of strain along z over strain along x. So, but from Hooke's law, since stress is proportional to strain, therefore stress along x is modulus elasticity times strain along x. So that stress along x is modulus of elasticity strain along x. Then strain along x is equal to stress normal to the x-axis over E from this equation here. Then strain along y, which is negative Poisson's ratio strain x. So negative strain y is also strain along z equals negative Poisson's ratio strain along x. And since strain along x is sigma x over E, so we replace sigma x or strain along x by negative sigma x over E. So these are the strains along x, along y, and along z. For uniaxial loading, the following are the strains. So strain along x, sigma x over E. Strain along y equals strain along z is negative Poisson's ratio strain along x, or negative Poisson's ratio sigma x over E from these results. So call this equation 2, uniaxial strains. For biaxial loadings by superposition method, the following will be the resulting strains. So if there is also tensile stress along y, So let's draw the figure first. This tensile stress along Y will cause negative strain along X. So therefore, the strain along X would become sigma X over E, then minus Poisson's ratio sigma Y over E. So sigma X would be, by superposition, sigma X over E minus Poisson's ratio sigma Y over E from the result here. So if there is stress along Y, then the strain along X would be negative Poisson's ratio strain along X is negative Poisson's ratio strain along Y over E. So that's why we have to subtract this term here. Then the strain along Y would be sigma Y over E, then minus Poisson's ratio sigma X over E. After we pattern it. Since there's no stress along Z, then strain along Z would be negative Poisson's ratio over E quantity sigma X plus sigma Y by superposition. So negative Poisson's ratio over E sigma X minus Poisson's ratio over E sigma Y, or simply negative Poisson's ratio over E quantity sigma X plus sigma Y. So strain along X after we factor out E is 1 over E quantity sigma X minus Poisson's ratio sigma Y. Strain along Y would be 1 over E quantity sigma Y minus Poisson's ratio sigma X, while strain along Z is negative Poisson's ratio over E quantity sigma X plus sigma Y. So that's it for this situation here. That would be the situation. So from strain sub X, which is sigma X over E, minus Poisson's ratio sigma Y over E, and multiplying everything by E, so we have E times strain along X equals sigma X minus Poisson's ratio sigma Y. So therefore, sigma X is E strain X plus Poisson's ratio sigma Y, and E times strain Y is equal to sigma Y minus Poisson's ratio sigma X. So sigma Y therefore is, which is equal to E strain Y plus Poisson's ratio sigma X from this equation here. So replacing sigma X by this value, so sigma X is equal to E strain X plus Poisson's ratio sigma Y, and sigma Y is given by this equation. Then we can factor out sigma X and write this as sigma X times quantity 1 minus, we have Poisson's ratio square here. So sigma X minus Poisson's ratio square sigma X equals E strain X plus Poisson's ratio E strain Y. Or factor out E, then we have strain X plus Poisson's ratio strain Y. Factor out sigma X on the left side, so we have sigma X quantity 1 minus V square equals E quantity strain X plus Poisson's ratio strain Y. Then we can now derive this formula here. Sigma X is for biaxial stresses or biaxial loadings, E times quantity strain X plus Poisson's ratio strain Y over 1 minus V squared. Similarly, strain along Y or stress sub Y, normal stress Y, is E quantity strain Y plus Poisson's ratio strain x over 1 minus Poisson's ratio square. So take note that for biaxial stresses, there's no stress along the z-axis. So that's for biaxial stresses. For triaxial loadings, the following will be the strains. So after we apply superposition method, so strain x would be sigma x over E minus 1 over E, or sigma x over E minus Poisson's ratio over E quantity sigma y plus sigma z. So that would be the, so 1 over E quantity sigma x minus Poisson's ratio sigma y plus sigma z rather. Then strain along y. This is for biaxial. So if it is triaxial, there is also tensile stress along z. So there will be third term which will cause the strain along x to contract further. So that's why we have a third term here of minus Poisson's ratio sigma z over E, which if we factor out 1 over E would become this expression here. So likewise, strain along y, we just pattern this formula, would be 1 over E quantity sigma y minus Poisson's ratio quantity sigma x plus sigma z. And strain along z would be 1 over E quantity sigma z minus Poisson's ratio sigma x plus sigma y. So this would be the resulting formulas, and we can easily derive this after we include the effect of the normal stress along the z-axis, normal tensile stress along the z-axis, which causes the strain along x to have the value negative Poisson's ratio sigma z over E, and this will be the result. The rest can be patterned. So note that equations 2.9 through 2.11 are valid for both tensile and compressive loadings. You just assign negative values for compressive stresses and contractions. For shear loadings, the distortion will be as shown below. So this is the shear strain. This is the original element. Then when distorted in the deformed shape, then we have this shearing strain. If within Hooke's law, stress is proportional to strain, then by analogy, shear stress is also proportional to shear strain. And the constant of proportionality is denoted by capital G. We call it the shear modulus of elasticity, or simply shear modulus, or modulus of rigidity. And gamma is the shear strain. So take note of the analogy. So shear stress is shear modulus times shear strain. That's the equation, and the relationship between shear modulus, Poisson's ratio, and Young's modulus of elasticity is rearranged in this manner so that you can easily recall it to give 2G quantity 1 plus V, 1 plus Poisson's ratio equals E. So I arranged the formula in this manner so that you can easily recall it. So that's it for this part. Then as an exercise, we will develop or derive formula for stresses for triaxial loadings just for one, then we can pattern the rest. So from triaxial loadings in an isotropic materials, the following formulas for strains were developed in the preceding slide. So if you can recall, strain along x is 1 over E quantity sigma x minus Poisson's ratio sigma quantity sigma y plus sigma z. Call that equation 1. Strain along y is 1 over E quantity sigma y minus Poisson's ratio sigma x plus sigma z. Call that equation 2. and strain along Z is 1 over E quantity sigma Z minus Poisson's ratio sigma X plus sigma Y. Call this equation 3. Then let us show that the corresponding normal stress sigma Y is given by sigma Y equals E over 1 minus 1 plus V, 1 plus Poisson's ratio quantity 1 minus twice Poisson's ratio, then times quantity 1 minus Poisson's ratio strain Y plus Poisson's ratio quantity strain X plus strain along Z. So we begin from equation 2. So we have E strain Y E equals sigma Y minus Poisson's ratio quantity sigma X plus sigma Z. And therefore, sigma Y is equal to E times strain Y plus Poisson's ratio sigma X plus sigma Z. So from 2.1, call this equation 2.1. Then sigma X can also be patterned is strain X plus Poisson's ratio sigma Y plus sigma Z. Then let's substitute this in 2.1. Strain or stress along Z is E strain along Z plus Poisson's ratio quantity sigma X plus sigma Y. Also substitute in 2.1 for these expressions here. So therefore, from 2.1, sigma Y equals strain E times strain Y plus Poisson's ratio quantity E strain X plus Poisson's ratio quantity sigma Y plus sigma Z for sigma X. Then for sigma Z, E times strain along Z, which is this, plus Poisson's ratio quantity sigma X plus sigma Y. So we have sigma Y here. We have Poisson's ratio square sigma Y, and we have Poisson's ratio sigma square sigma Y. So sigma Y minus Poisson's ratio square sigma Y minus Poisson's ratio square sigma Y equals E times strain Y plus Poisson's ratio E strain X plus Poisson's ratio square sigma Z, then plus Poisson's ratio E strain along Z plus Poisson's ratio square sigma X. Because we already factor out, we already transpose sigma Poisson's ratio square sigma Y twice here. So simplifying, sigma Y times quantity 1 minus 2 times Poisson's ratio square, because we can combine these two terms here, and factor out E. Then we have sigma Y plus Poisson's ratio sigma X, strain X rather, then plus Poisson's ratio strain Z. Then we have Poisson's ratio square quantity sigma X plus sigma Z for this third and last terms. So we break this into, we break Poisson's ratio square into Poisson's ratio times Poisson's ratio quantity sigma X plus sigma Z in this manner. And we substitute the value of Poisson's ratio quantity sigma X plus sigma Z from this equation here as sigma Y minus strain YE. So Poisson's ratio sigma X plus sigma Y from this equation is sigma Y minus E times strain Y. Then let's substitute the value of this expression, which is this expression here, as sigma Y minus E times strain Y into this equation. So sigma Y quantity 1 minus 2 times Poisson's ratio square equals E. So we just copy this, then plus Poisson's ratio times this quantity sigma Y minus E times strain Y. So again, there is sigma Y here. Let's transpose this to the left. So we have sigma Y quantity 1 minus 2 times Poisson's ratio square minus Poisson's ratio, because there is sigma Y here, equals, we copy the first term, then the second term is negative Poisson's ratio E strain Y. Then rearrange sigma Y times quantity 1 minus Poisson's ratio minus 2 Poisson's ratio square equals E. Then we have for strained Y, common is E and strained Y for this term and that term. So we have E common to all terms, then we have 1 minus Poisson's ratio. Then for these two common Poisson's ratio, then strain X plus strain along Z. So we can factor this as sigma Y times 1 plus V, then 1 minus 2 times Poisson's ratio equals E, and quantity 1 minus Poisson's ratio strain Y plus Poisson's ratio quantity strain X plus strain along Z. So finally, this formula is after we divide everything by 1 plus Poisson's ratio times 1 minus twice Poisson's ratio would now be this result. So that's the stress normal to the y-axis, stress on the y-axis. So similarly, sigma x is equal to E over 1 plus Poisson's ratio times 1 minus twice Poisson's ratio, open quantity 1 minus Poisson's ratio strain along x plus Poisson's ratio strain along y plus strain along z. And sigma z is, we just copy this, and quantity 1 minus Poisson's ratio strain along z plus Poisson's ratio strain x plus strain y. So that's it. We have shown that stress along y is really given by this formula for triaxial loadings. The steel truss supports a 27 kilonewton load. The cross-sectional areas of the members are 320 mm square for AB and 480 mm square for BC. Compute the horizontal and vertical components of the displacement of B using modulus of elasticity of 200 gigapascals. So here is the given figure. Let's compute the forces of members AB and BC. So let's assume tension, just like in statics. Call that PBA and PBC. So the slope is 3 vertical for 5 hypotenuse. 3 vertical for horizontal, then 5 hypotenuse. These are the lengths. So at B, summation forces y equals 0. The vertical component of PBA is PBA times 3 over 5, then minus 27 equals 0. So solving for PBA, PBA is equal to 45 kilonewtons, and it is in tension because the result is positive. Likewise, summation forces X equals 0 still at B. Then we have 45, horizontal component of PBA is 45 times 4 over 5 plus PBC equals 0. So PBC is negative, so it is compression. It is negative 36 kilonewtons, so it is compression. So computing for the deflection, which is force length over AE. So deflection BA is 45,000 newtons, length is 4.5 meters or 4,500 mm divided by area of AB, which is 320 mm square, and modulus of elasticity 200,000 megapascals or newton per mm squared, so that the deflection for member BA would be in mm. So deflection BA is 3.164 mm. Then deflection BC is negative 36,000 or 36 kilonewtons, 36,000 newtons, length 3.6 meters or 3,600 mm. Area is for 80 mm square, modulus of elasticity 200,000 newtons per mm square or megapascals. So in mm, it is negative 1.35 mm. So the principle is to locate the final position of B for we allow B to elongate along AB, then we draw perpendicular line towards the final position of B. So that's 3.164 for deflection along BA. Then we draw a line perpendicular to this end. Then also for BC, it is contraction 1.35. So it is contraction 1.35, and because this is horizontal, we draw vertical line to meet at this point. So this is the final position of B, exaggerated B prime, and this is the displacement of point B, that one. But we are only asked to compute for the horizontal and vertical components of displacement. So obviously, the horizontal component of displacement is 1.35 rightward, while the vertical component of displacement is this total vertical movement. So that's delta B. So that's vertical, that's perpendicular rather. And the angle here is also equal to this angle here, which I call theta. So this is also theta. This is also theta, the angle between the vertical and perpendicular to this incline by principle. So let's call that distance y1, and this one is x1. So this total horizontal movement is x1 plus 1.35, and call this y2. So that the vertical component of the displacement of B would be y1 plus y2 downward. So y1 is 3.164 sine of theta, and sine theta is equal to 3 over 5 from this figure, from the slope. So y1 is equal to 1.8984 mm. Then tangent of theta is x1. So let's solve for x1 first. x1 is 3.164 cosine of theta, and cosine theta is 4 over 5. So 3.164 times 4 over 5 is 2.5312 mm. Then tangent of theta is x1. It is equal to 3/4. Tangent theta is 3 over 4, the slope. And this is also equal to x1 plus 1.35 over y2. So y2 can now be solved. y2 is equal to 5.175 mm. So finally, the horizontal component of displacement at B is 1.35 mm rightward, and the vertical component is downward, y1 plus y2. So 1.8984 y1 plus y2, 5.175. So delta B vertical is 7.0734 mm downward. So take note that these components of displacements can also be computed by virtual work or by Castigliano's second theorem in structural theory subject. But this is the technique in the mechanics of materials.